Hi there, and welcome to part 1 of Arithmetic and Geometric Sequences. What you're seeing here is part of the 8th grade formula sheet. The patterns that we explore today are going to help you to understand how to successfully use this formula sheet on the MCA. How are linear and exponential functions connected to arithmetic and geometric sequences? That's what we're going to explore today. So what I have for you here are 2 arithmetic sequences. And if you take a look at these numbers here, and here, they're a sequence of numbers that forms an arithmetic pattern. So we're going to investigate here to figure out what makes this sequence of numbers arithmetic. What does it look like when we graph it? What type of function rule could we write? Just some generalizations we can make about arithmetic sequences in general. So looking at the numbers, what pattern do you see happening here to get to the next number? You're probably thinking it's plus 2, plus 2, plus 2. Repeated addition. Absolutely. Arithmetic sequences can form a repeated addition pattern in the numbers. So what we're going to do here is take this sequence of numbers and we're just going to put it into a table so we can graph it and see what the graph looks like. So we're going to say that term 0 is the first term in the sequence. So term 0 right here is the number 1. And then term 1 in the sequence, we'll say that's 3. Term 2 is 5, 7, and 9. So I just took the sequence of numbers and I put it into the table. Now let's graph these as ordered pairs and see what happens on the coordinate plane. Go ahead and graph along with me in your notes. And you should see that if you connect the points, you're going to get a straight line, which means this is linear, which means that we can write a linear function rule for the table of values and for the sequence. So remember, linear function rules, they can either start f of x or they can start y equals. It doesn't really matter. But we know that that first number is our slope times x, and then we add or subtract the y-intercept. So just by looking at the table of values, you can see that the y-intercept when x is 0, that's 1. And the rate of change, the slope, change in y, which is up 2, and change in x, which is plus 1. So 2 over 1 would be a slope of 2. And then you can check your rule. So just try to get from x over to y. It says to take x, multiply it by 2. That would give me 8, and then add 1. And you see how that gets you over to 9. So there we have our linear function rule for that arithmetic sequence. Now let's take a look at the second arithmetic sequence. This sequence of numbers, 15, 12, 9, 6, and 3. What pattern do you see is happening in the numbers to get to the next one? If you said repeated minus 3, you're right. A pattern that's repeated subtraction is also an arithmetic sequence. Think about when you first learned math. You learn addition and subtraction, basic arithmetic. Arithmetic sequences are made by constant adding and a constant subtracting pattern in the numbers. So let's take these numbers now, let's put them in the table, the 15, 12, 9. So let's just say that term 0 is 15, term 1 is 12, 9, 6, and 3. Now let's take these as ordered pairs and we're going to graph them on the coordinate plane. So 0, 15, and then if you connect them, you're going to see that again, they make a straight line, which is linear. So again, with this arithmetic sequence, we see a linear relationship. So let's write the function rule. We can either use y equals or f of x. So we have our slope, mx plus b. Our y-intercept is the b, and of course, that's the 15. That's where it touches the y-axis. So that's 15. And then your slope, your rate of change, looks like we're minusing 3, right? That was our pattern. And then the x is plus 1. So minus 3. So y equals negative 3x plus 15. So with arithmetic sequences, we're going to see constant minus patterns or constant addition patterns. We're also going to see straight lines, linear. We're going to have linear functions. Okay, now let's go ahead and explore geometric sequences. All right, so here's our first geometric sequence, 1/4, 1, 4, 16, and 64. What's happening to get to the next number? You're growing, right? It's multiplication though. Do you see how it's a constant times 4 times 4 times 4? The pattern is multiply by 4. In a geometric sequence, you're going to see a multiplicative pattern. So we see multiply by 4. Let's take that sequence, we're going to put it into a table. We're going to say that term 0 is 1/4, term 1 is 1, then 4, 16, and 64. Okay, now let's graph it and see what type of line it's going to make. So 0, 1/4, right about here, 1, 1, it's way down here, 2, 4, well, 4 is halfway between 0 and 8, 3, 16, whoa, now we're getting up there, in 4, 64. Oh my gosh, we're like way off, way up here if you can even see that. What's happening? Very slow growth, but then very quickly. What type of what type of growth is that? Exponential. Absolutely exponential. That's exponential growth. So if I'm going to write a functional, remember that's a times b to the power of x. The a is the y-intercept, which is 1/4. And the b is the multiplier, which is times 4 times 4 times 4. So there's the function rule. It's an exponential function rule when we have a geometric sequence. Let's see if the same thing happens over here. 20, 10, 5, 2.5, and 1.25. What's the pattern? What's happening to get to the next number? Now you might see this as division, right? But it also can be seen as multiplication. If I'm taking half of means to multiply. Half of is multiplying by half. Of course, that's the same thing as dividing by 2, but it's multiplication times half. So again, in a geometric sequence, you're going to see that multiplication pattern in the numbers. It may look like division, but it's just probably multiplying by a number smaller than 1. Let's take the sequence of numbers. We're going to say 20 is term 0. Term 1 is 10, 5, 2.5, and then 1.25. Okay, so let's graph it and we're going to see what happens here. 0, 20, 110. Kind of reminds me of Half-Life. 2, 5. Whoops, I made a mistake on that one. 2, 5. And then 3, 2.5. 4, 1.5. Oh boy. So notice here with this decay, here we fall very quickly and then slowly. This is a perfect example of exponential decay. This is an exponential decay sequence. And so we can write an exponential function for it. All right, so the a value is the y-intercept, the starting amount, which is 20. Oh my gosh, I don't even know what that is. That's a 2. And then the multiplier is going to be half. There we go. There's our function rule. So notice here with geometric sequences, we're going to see patterns that are multiplication. We're also going to see lines that are curved, like exponential growth or exponential decay. And we're also going to see function rules that are exponential. So those are all things I want you guys to notice here. Okay, let's do a quick recap of arithmetic next to geometric sequences. Let's focus on arithmetic first. So with arithmetic, let's think about what do the graphs look like? Is it linear or exponential? What patterns do we see? And what does the function look like? These are all the things we need to know about arithmetic sequences. So with an arithmetic sequence, we know that the graphs are going to be a straight line. They're going to be linear. We can have a positive slope, negative slope, whatever, horizontal, vertical. They're just going to be straight lines, which means they're linear. So let's circle linear. The patterns that we're going to see in the sequence of numbers, it's going to be either constant adding or constant subtraction. Remember basic arithmetic. When I learned basic arithmetic when I'm a little kid, I learned how to add and subtract. And then the function rule will always be linear, which is just basically y equals mx plus b. Okay, that's arithmetic. And actually, we've done that before earlier in the school year, chapter 4 and chapter 5. All right, geometric. Let's take a look at the graphs and all the different patterns we see. With geometric, what do the graphs look like? Let's make a quick sketch. Now with geometric, we're going to see exponential, either growth or decay, the curved lines. We're going to circle exponential. What patterns are we going to see in the numbers? Multiplication. It may look like division, but think we can just see it as multiplication because we're multiplying by a number smaller than 1 if you see a division pattern. So multiply. And the reason why I like to just stick with multiply is because the function rule is exponential. And with an exponential function, you're taking a times b to the power of x. Okay, so here we've got it, everybody. A quick recap, side by side, arithmetic and geometric. So now, does the formula sheet make sense? Does it make sense that arithmetic sequences are paired up here with a linear function? Whoops. Does it make sense that geometric sequences are paired up with an exponential function? I don't know why it keeps doing that. So hopefully that makes sense to you why this is what the formula sheet looks like. So now what we're going to do, ooh, isn't that cool? A little spinny light bulb. Now what we're going to do is actually try this. See if you can tell the difference between the two. So label each table as either arithmetic or geometric, and then write the function rule. So for our first table over here, let's get the marker going on over here. I can see that like the x values, do you see how the x values in every single table are always going up by 1? So that's just consistent. Okay, so let's just look at the dependent variable, the y. So let's look at the pattern that's happening here. It's very consistent. We're minusing 2, minusing 2, minusing 2. So a constant subtraction. So what type of sequence of numbers would that be? If you said arithmetic, you are right. So then let's write a function rule for that. Remember, that's y equals. We can see that our slope, our rate of change here is minus 2, minus 2, minus 2. And we can see our y-intercept is negative 2. So let's put it all together. Function rule, negative 2x minus 2. Here's our slope, and here's our y-intercept. Okay, next one. So let's look at our pattern in the y. Very constant. Ooh. Do you see it as divide by 3? Me too. But let's think multiplication. What could we be multiplying by? If we're dividing by 3, we're really multiplying by a third, right? A third of, a third of, a third of, a third of. So if you said geometric, you are right. So if it's geometric, we should be able to write a exponential function. So remember, that's y equals a times b to the power of x. So go back up into the table. Here's your y-intercept. You know that the pattern is times 3 every single time. Can you write the exponential function for it? Is this what you had? Your 81 is your y-intercept, and it's multiplying by a third every single time. Okay, let's go to the third one. Take a look at the pattern. It's growing really fast, isn't it? Do you see how it's multiplying by 6 over and over and over again? So is that arithmetic or geometric? If you said geometric, you are right. So again, that's going to be an exponential function just like the last one. So we've got our multiplier, our b value. Now we need to look at our y-intercept. So your y-intercept here is 1. So if I wrote the exponential function, it would look like this. 1 was my y-intercept and 6 is my multiplier. Now, do you see how if you multiply by 1, the 1 would kind of go away? So even if you wrote y equals 6 to the power of x without the 1, it's still perfectly fine. Okay, let's look at the last one. Look at the pattern. Might be easier to see it in the positive numbers. Do you see how it's adding 4 every single time? So is that arithmetic or geometric? Constant addition? Yeah, if you said arithmetic, you are right. So if it's arithmetic, then we've got to have a y equals mx plus b equation. So b is your y-intercept, so go back up here and find it. You've got your rate of change, your slope, adding 4. So put it all together in an equation. Is that what you had? Yep, so 4 is my rate of change, minus 6 is my y-intercept. So here we've got arithmetic, geometric, Lots of patterns going on. Okay, I think we're ready to take what we've learned and apply it. So let's see if we can look at some examples together now. Okay. In these two examples, we want to describe the sequence. And I accidentally hit the button, so you get these little arrows here. Whoops. Okay, so let's describe the sequence. We've got this sequence of numbers here, 1, 3, 9, 27. And we've got 4 choices. So if we're going to describe the sequence, we need to determine what's happening in the sequence. So to get from one number to the next, to the next, to the next, what's happening? The numbers are increasing, they're growing, so it's either got to be add or multiply. Do you see what it is? Yeah, it's times 3 times 3 times 3. So now let's take a look at our choices. We have 4 different choices. 2 of them aren't even possible. Can you determine what's not even possible? Yeah, do you see these 2? You can't be arithmetic and nonlinear, and you can't be geometric and linear. That just doesn't work. So I can automatically cross off those 2. So either A, it's geometric, which means it's nonlinear, or it's arithmetic, which means it's linear. Which one is it? Well, it's constant multiplication. So that's geometric. So and I can also see up here that I have my formula sheet, so you can look at the formula sheet to determine what's going on, right? Okay, let's look at the second sequence of numbers. So we got 17, 12, 7, and 2. What's going on to get to the next number? 17 to 12 to 7. They're getting smaller, so it's either going to be subtraction or division. Do you see how it's minus 5, minus 5, minus 5? Okay. So again, look at the answer choices. There's 2 of them that aren't even possible. You can't be arithmetic and nonlinear because all arithmetic sequences are linear, right? So those last 2 don't even make sense. So I've either got this pattern's either geometric or it's arithmetic. And because it's the minus 5 over and over again, it's arithmetic, which means it's going to be linear because all arithmetic sequences are linear. Okay, let's take a look at number 3 and 4. Here we're being asked to identify the correct form of the sequence. So let's look at the first one, 3, 9, 27, and 81. What's happening to get to the next number in the sequence? It's growing. Do you see how it's tripling? It's multiplying by 3. What does that mean? What type of sequence is it, arithmetic or geometric? Well, because it's multiplying by 3, it's geometric. Now take a look at your answer choices. Of those answer choices, which is the only one that's a geometric sequence? Now look up at your formula sheet. Geometric sequence. All geometric sequence equations are going to look like this. So take a look through your answer choices. Which one looks like f of x equals a times b to the power of x? Which one of them looks like an exponential function? Well, that would be b. It's the only one. So I'm using my formula sheet to help me out with this. Okay, let's look at the next one. Here's my next pattern or sequence. Let's determine what's happening to get to the next number. 7 to 11 to 15. It's increasing, so it's either adding or multiplying. You see how it's adding? So constant adding. What type of sequence is that? Arithmetic or geometric? Well, that would be arithmetic. So let's take a look at the answer choices. What would be the correct form of the sequence? Well, look at your formula sheet. All arithmetic sequences, their equations look like this. Linear. Y equals mx plus b. So look at your answer choices. Which one is the only one that looks like that? The first one, A. Okay, so you see how your formula sheet can help you out a little bit with this. All right, I think we're getting pretty good at this. Number 5. What is each term multiplied by to get to the next term in this geometric sequence? Well, it makes sense as a geometric sequence because it's saying that you're multiplying to get to the next term. I'm given an empty box, so I want to put the answer in that empty box. You may see this as division. Do you see divide by 3, divide by 3, divide by 3? But we're being asked, what are we multiplying by? Well, dividing by 3 is the same thing as multiplying by You got it. A third. A third of, a third of, a third of. So in the box, what am I multiplying by? I'm multiplying by 1/3. So you're just figuring out what that b value is, that multiplier you're taking a third of. All right, that wasn't so bad. In the video, we are going to be skipping number 6. That's only an in-class problem. Okay, on number 7. What is the 7th term in the sequence? Well, here it's not telling us if it's arithmetic or geometric, so we have to decide. Here's our sequence. How do we get to the next term? Well, do you see how we're increasing? That means we're either adding or multiplying. That's how numbers get bigger. And so you can use your calculator and decide. It looks like for the first two numbers, you could be adding 3, but then that doesn't continue. Try multiplying. What about 1.5 times 3? There it is. And then if you take 4.5 times 3, it continues the pattern. Okay, so we want the 7th term. Well, here we've got term 1, 2, 3, 4, 5, 6, 7. So maybe what I do is I use my calculator and I hit times 3, times 3, times 3 to get to that 7th term. And when you do that, you are going to get answer C. So we looked at the sequence, we determined that it was geometric. That helped us to figure out what the 7th term was. We just continued the pattern and we figured it out. In number 8, we're going to need to use the formula sheet to help us as well. Which expression forms an arithmetic sequence when x equals 1, 2, 3, and 4? So remember, an arithmetic sequence is a constant add or subtract pattern between the numbers. If we plug in the x values of 1, 2, 3, 4, which one of these expressions would give us an arithmetic sequence? Well, there's kind of a way you can cheat a little bit with this. We're looking for arithmetic sequence. Look at your formula sheet. All arithmetic sequences are linear. So mx plus b. Take a look at your answer choices. Which one is the only one of the expressions that looks like that? Yeah, it's C. Look at this. If I put y equals, there's your mx plus b. Right there. It's the only one. So right there, the formula sheet pretty much gives it away for you. Now, if you were actually to plug in these x values in to this expression for x, you're going to see that it's going to give you an arithmetic sequence, a sequence of numbers that have an add or subtract pattern. But I wouldn't even need to do that. I could just use my formula sheet to figure it out. In number 9, which function forms a geometric sequence when x is 1, 2, 3, and 4? Okay, so let's see if we can use our formula sheet for this one too. It says geometric sequence, and we're given now function rules. See how they all start with f of x? Okay, let's go up to our formula sheet. Geometric sequences always have a function rule that looks like this. So look at the answer choice. The answer choices. Which one looks like that exponential function? Now look really carefully. It's an exponential function, so it has an exponent in it. But what specifically is the exponent? It's an x, which leaves the only answer to be b. It also has an exponent of x. Okay, that would be the answer. Now, if you were to plug in x is 1, x is 2, x is 3, and 4 in for the x in this function, it's going to give you a sequence of numbers that is geometric. But you wouldn't even need to do that. You could just use the formula sheet. On number 10, we're asked to label each of the functions as linear or nonlinear. So again, we can use our formula sheet to help us. We know that everything that looks like this, y equals mx plus b, is arithmetic and also linear. We know that everything that looks exponential like this is nonlinear. Remember, it makes that curved growth or decay, right? So use that formula sheet to help you out. Let's go over here to this first one, f of x equals 3. Or you can think of it y equals 3, if that helps you. Is that a linear equation or an exponential equation? Well, there's no exponent in it, right? Remember y equals 3. If you were to graph that on a coordinate plane, you go up to 3, make a point, and it would be one of those really nice horizontal lines, right? Yeah, it's linear. It's totally linear. Okay, there's no exponents in it, so it's not nonlinear. Okay, so now let's look at the second one. This one right here. What do you notice? What does it look like? Which equation in the formula sheet? Do you see how it has an exponent in it? Right? Now, it doesn't have an exponent of x, so it's not going to be an actual exponential growth or decay curve, but it's not going to be straight. Remember, linear means a straight line. And we learned way back earlier in the year that if there's an exponent in it, it's not linear. So right now, I know that that's going to be nonlinear. The next one. Ooh, we talked about this in the beginning of the year also. I don't know what happened with that circle. Here we have an x in the denominator. There's no exponents. There's no exponents in it, but the x is in the denominator. Look at the arithmetic sequence. Look at this one. Do you see how the x, if I make this a fraction, is in the numerator? What would happen if I move this x to the numerator? Think about your exponent rules. If I did that, if I move the x to the numerator, right now it has a positive 1 exponent. If I move it up to the numerator, it's going to have a negative 1 exponent. And that's definitely not linear. No way. You can't have an x in the denominator. So I'm not sure if you remember that from earlier this year, but anything with an x in the denominator is non-linear. We graphed them earlier in the year. Okay, last one here. Do you see any exponents in it? Me neither. What number would be in front of the x? It's in the numerator, a 1. If I even took these two and I switched them around, it would be 1x over 4 minus 2/3. This would be my slope. This would be my y-intercept. It's linear. Okay, so if it's nonlinear, I'm looking for an exponent in it or even an x in the denominator. If it's linear, I'm just looking for a y equals mx plus b. So the formula sheet can kind of help you with that a little bit. Also, you're using things that we learned earlier in the year. Okay, so to summarize, really you should be able to look at that chunk of the 8th grade formula sheet and be able to tell how arithmetic sequences and linear functions are connected and how geometric sequences and an exponential function is related. So thank you for joining me today. I hope you've learned something and make it a great day.